Okay, so hello everyone. Again, thanks for joining our North American JMAG user conference. My name is Brian Kowalczyk. I'm the JMAG coordinator for university support. Today we are privileged to have as our next speaker, Nanjun Tang. Nanjun comes to us from the Illinois Institute of Technology, Chicago, Illinois. Nanjun received his BS and MS degree in electrical engineering in 2013 and 2015 respectively. He is currently pursuing his PhD degree in electrical engineering with Illinois Institute of Technology. His research interests include electric machine design and drives, with a focus on theory and development of improved electric machine windings to reduce harmonic content. And he will be sharing or be presenting on this topic today. As a reminder, attendees can enter questions through the Q&A tag at the bottom of the Zoom screen during the presentation, and we'll hope to have time at the end to answer some questions. So with that, I'd like to welcome Nanjun. Welcome.
Thank you, Brian, for the kind introduction.
Of course.
Good afternoon and good morning to those of you on the West Coast and the rest of the world. My name is Nanjun Tang. I hope you are all safe and healthy. My talk today is about electric machine windings with reduced space harmonic content. Here's a brief preview. We'll do an introduction and then look at mathematical representation windings, solution techniques for the reduction of space harmonic content, and the application of a mixed layer winding on a traction motor for performance improvements. Now let's begin with the background information. We know that electric machines are important in many industries for the consumption, generation, and interchange of power. In particular, the winding has a critical role for the energy conversion. The focus of this study will be symmetrical three-phase AC windings. There are two major categories: distributed windings and fractional slot concentrated windings, where the slots per pole per phase number, or the SPP, is greater than or equal to 1 for distributed windings, or less than 1 for fractional slot concentrated windings, hence its name. We see that distributed windings have overlap and connections, whereas fractional slot concentrated windings, they have non-overlap and connections. Here, this distributed winding with segmented coil parts inserted from one end and welded on the other end. It's one of the newer manufacturing technologies in EV, HEV motors. It's sometimes called the hairpin winding. The magnetic field of a 12-slot 10-pole double-layer fractional slot concentrated winding is shown here as an example. It contains many harmonic orders. Different orders have different magnitudes and move in either of the two directions. Here, the fifth order, the orange one, is working harmonic, and it's the component that produces the average torque. The others are all non-working harmonics, and they cause side effects like torque ripple, power losses, and noise and vibration. We would like to reduce non-working harmonics and make the overall magnetic field as sinusoidal as possible. Conventional methods to reduce space harmonics, including choose a higher SPP, short pitching, skewing. Beyond those, a more challenging topic is how to adjust coil turns and slot distribution to reduce the space harmonic content. We also show that it can be combined with skewing or star-delta connection, which is in effect a dual three-phase connection, to further enhance the harmonic reduction. In order to do that, we first need a general mathematical representation of windings. This mathematical representation, we want it to be applicable to all windings. distributed windings, differential slot concentrated windings, different slot pole combinations, etc. It will be based on the winding function, which contains the information of spatial placement of conductors and their polarity. We also want this representation to be as concise as possible. We only draw the winding function for a one unit machine, and we call that 360 degrees. So if we have 24 slots, 4 poles, we do this, and we decide that the unit machine is 12 slot, 2 pole, and we draw the single phase winding function for that. The reason of choosing one phase, for example, phase A, instead of all phases is that the shape will be time independent. It will be more recognizable. Also, we usually assume all cores have just one turn to make the results easily scalable. Here we draw the winding functions of a lot of different windings to see what's in common and what are different. Although these windings can be distributed windings or differential slot concentrated windings, and they can have different slot pole combination and SPP. They can have different coil page, different number of layers. Some may have even order harmonics, some may not. So this one, and this one, they have even order harmonics. The remaining, they don't have even order harmonics. Although they are so different, they all have something in common. They all have even symmetry when you shape them horizontally, so that the vertical axis is the axis of symmetry. And due to this, only half the unit machine we use the right half is sufficient for a complete representation. We call the harmonic orders by integers starting from 1, and P0 will be the working harmonic. As a side note, sometimes we have half-wave symmetry. Sometimes we don't, meaning the winding has even order harmonics, second, fourth, etc. By taking advantage of those similarities, we came up with a way that is uniform and very concise to represent windings. We use 2 lists of variables. One is the slot position angles, for example, alpha 1, alpha 2, and alpha 3. The other are levels. Here, M1, M2, M3, and M4. Then we'll show how the harmonic magnitudes, the winding factors, can be written out as function of these quantities. What we do is we find an elementary building block looking like this. There's a parameter here, alpha, that shows where the steps happens. And then any winding can be written as a linear combination of this elementary building block. The coefficients and the parameters are just the levels and slot position angles we have figured out earlier. Then if we insert the Fourier series of the building block into this equation, after some arrangement, the harmonic information of winding is clear. We have this straightforward expression for the magnitude of every harmonic order. At this point, we can summarize the closed form expressions that are available. We have the magnitude for an arbitrary order, and in particular, we can let n be P0 to have the working harmonic magnitude. We can pre-unitize by taking the ratio of Mn and MP0. We also have the working general form of winding factor of any order and the working harmonic winding factor. We have finished the mathematical representation. It's a good analysis tool. Let's work at some examples and demonstrate some different solution techniques to show how it can be used as a design tool as well to find windings with reduced space harmonic content. For conventional windings, it's a case that slots are equally spaced and coils are of the same number of turns. Once the number of phases, slot pole combination, number of layers, and the coil pitch are selected, the winding layout and its harmonic content are fixed. If we take the extra step to vary the slot distribution and coil turns, and we do it properly, we end up with windings with reduced space harmonic content. We can reduce or eliminate certain non-working harmonics, maximize or control the winding factor for the working harmonic, and we can improve the machine performance, reduce the torque ripple, etc. So how do we formulate the problem? What are the available solution techniques? Let's look at this example. We start with the SPV3 single layer distributed winding. Conventionally, with equally spaced slots and same coil turns, the slot position angles and levels are like this. If we look at the harmonic spectrum, the fifth and the seventh harmonics have larger magnitude, that percentage of the working harmonic. And they will cause the sixth order torque ripple in the torque output. Our goal is to eliminate both the fifth and seventh harmonics, make them zero magnitude simultaneously. To formulate the problem, we take the closed form expressions we saw on a previous slide and write one equation for the working harmonic winding factor and one equation for each of the non-working harmonics we want to reduce. To make it easier to start with, we assume the coils are still the same turns, but we want to vary the slot distribution. For example, we want to maximize, we want to eliminate both the fifth and seventh harmonics while having control of the working harmonic winding factor. These simultaneous equations can be solved numerically, but that may fail if the initial guess is too far away. To avoid that, we can use algebraic methods. For example, Grobin basis, which is a tool in commutative algebra to solve simultaneous polynomial equations. We use this multiple angle formula to convert these equations to polynomials of sin alpha 1, sin alpha 2, and sin alpha 3, which we write as x1, x2, x3 for short. Then we solve them by finding their Grobin basis, which will be in this triangular form, so the unknowns can be solved one by one. And some winding factor, it may have no solutions, and we want to repeat this until we find the highest possible winding factor. For this example, the maximum winding factor is this number. It has 4 solutions. We are showing the first and the fourth solutions here, which happen to have the same harmonic spectrum. Indeed, we eliminate both the fifth and seventh harmonics simultaneously. But it may not be that satisfactory since it has those even order harmonics. So can we do better than that if we let both angles and levels or equivalent the coil turns be the design variables? This time we write the equations in this matrix form with the coil turns as explicit variables. We see they are homogeneous, but the coefficient matrix has some unknowns. We solve this by going through a repeated 2-stage process. Remember that we said we want to avoid even order harmonics. in the spectrum. So we impose this even harmonics free condition, which we can prove that it's the equivalence of half-wave symmetry, and then start by first reducing the rank of this coefficient matrix, and then check its null space. We repeat until a meaningful solution is found in the null space. At that point, the matrix and the solution are decided, and we found a new winding. Here we show the new winding on top of the conventional one we started with. The winding function looks like this. It corresponds to phase A. If we draw the winding layout, we shift phase A by 120 degrees to the right and to the left to complete the other two phases. One thing special about this winding is that it's in this mixed layer structure. We have 1 and 2 coil sides in every other slot. Also, there are 2 coil sizes. They have the turns ratio of 1 to √3. The harmonic orders 5, 7, 17, 19, those are all eliminated. We don't have any orange bars here, no orange bars here. Actually, these orders are associated that we can show in the matrix form. Just a moment later, we'll simulate this mixed layer winding and show how it reduces EMF harmonics and top ripple. We'll briefly show another two solution techniques since we have our very handy closed form expressions. The first one is numerical optimization. They can be used as objectives and constraints. The slot position angles and levels are variables. And if we use the even harmonics free condition, we are left with fewer independent variables. For example, we say we want to find the space, the shape that maximize the winding factor for the working harmonic, but we want to the fifth and seventh harmonics to be very small, 100,000 the working harmonic. That's basically to eliminate them, and we got the same results here as a mixed layer winding. Then we can also visualize the solution space. We said that we are left with fewer variables if we impose the even harmonics free condition. If we only have 2 or 3 variables, then it's very straightforward to draw the contour plots. With these expressions, we draw the 2D contour plots for the winding factor, the per unit times magnitude for the 5th and 7th order harmonics. Then we overlap this one and this one to see if the 5th and 7th orders can be eliminated at the same time. It turns out that it's compatible. And we can visually tell it's somewhere near here, maybe 60 degrees and 0.6 turns ratio. It won't be exact as the algebraic method or numerical optimization, but it makes it crystal clear that how those metrics change with the design variables and their compatibility. All right. Finally, we have worked through the theory part, and let's look at some results if that's more exciting. It's the BMW i3 motor, and we check out the mixed layer winding we just designed. So the BMW i3 motor is a traction motor used on board that vehicle. It's a 72 slot, 12 pole interior permanent magnet synchronous motor. The cross-section looks like this. The winding is a conventional SPP2 single layer winding, which is quite popular with EV, HEV applications. The rotor is an IPM rotor with 2 magnet layers. It's supposed to deliver at least 250 Newton meters at the corner speed of 4,500 RPM. High torque density and high specific power. We're going to check this working point. In JMAG, we built this partial model, which is 1/12 of the whole thing, or one pole model. What we are looking at here is first we check the performance with the original winding, the single layer winding. We compare 2 options, a skewed rotor and unskewed rotor. The real thing is step skewed with 6 segments. For the EMF waveform, we see the major harmonic orders are the 5th, 7th, 11th, and 13th. After skewing, the 11th and 13th are reduced a lot, but we are still left with the 5th and 7th. What we need to say here is that this motor design at this working point happens to have very small 5th and 7th, but that's not the case for every motor and every working point. But so we still want to find a way to reduce them, and skewing alone doesn't solve this problem. And if we look at the torque waveform, the 12th order torque ripple is reduced a lot by the skewing, but the 6th, that's not a huge reduction. So maybe we can improve this further using a new winding, the mixed layer winding. Just to remember, the layout of the mixed layer winding looks like this, and we set it up in JMAG using the FEM coils and the circuit editor. We chose the coil turns for the larger and smaller coils so that they're close to the ideal turns ratio, and also has a similar total number of turns as the original single layer winding. We adjust the excitation current accordingly so the ampere turns are the same as a single layer winding for a fair comparison. We'll predict that the 5th and 7th order harmonics in the back EMF and 6th order torque ripple will be taken care of with this winding. Is that true? So the results are here. With the mixed layer winding, the 5th and 7th order harmonics in the back EMF and the 6th order torque ripple are basically eliminated regardless of whether it's skewed rotor or not. That's a great thing if you are at a different working point of this motor or a completely different motor, where we found that it's dominated by the 6th order torque ripple. Then the mixed layer winding will be quite reliable for their reduction. For this working point, the rotor is already skewed, and when combined with the mixed layer winding, the EMF is very close to being sinusoidal, less than 1% THD. The torque output is also quite smooth. Also, you can compare all 4 options, mixed layer, single layer, skewed, unskewed, to get a better picture. All right, we are close to the end, and just very briefly, more applications of this framework. So if we are able to limit the torque ripple very well, then other metrics have more space for improvements. If it's a multi-objective optimization, it improves the Pareto front. Also, if we can use a phase shift, some version of the dual three-phase connection, then the working harmonic winding factor, it can even increase. This is not the motor we simulated. It's a fractional slot concentrated winding, 24 slot, 22 pole. We have 2 winding subsets and 30-degree excitation phase shift. The result is that we increase the working harmonic winding factor and the average torque output while eliminating 3/4 of all non-working harmonic orders and the torque ripple. To summarize, we talk about the winding representation, the framework and solution techniques, and we look at some simulation results of the mixed layer winding for space harmonic reduction. We have some articles on this topic if you are interested. Thank you for watching. I think we'll have a live Q&A session. Any questions, comments, appreciated. Thank you.
Nanjun, thank you.
Thank you.
Of course. And we can take a question or two. We have a couple minutes left.
Right.
Attendees can hit the Q&A tag at the bottom of the Zoom screen there, and maybe type in a question. We can take a couple.
Do I need to stop sharing my screen?
You know what? Leave your presentation up just for another minute or two.
Right.
Maybe a question might point to a certain slide you can answer with. Maybe.
Mm-hmm.
Yep, let's see. No questions yet.
That probably means we are crystal clear.
Yeah, we'll hold on for a minute here. So I'm getting a question here. Actually, I think my vet is bringing it in from potentially Huva. It says, it is mentioned, if you can listen to this, Nanjun, it is mentioned on session brief that windings are designed in this study with the 5th and 7th order space harmonics. What is the 5th to 7th order space harmonics? They're asking, what is that?
Right. So imagine we have a 12-slot 2-pole machine. Then the first order means we have 2 poles along the machine circumference. The second order means we have the wavelength is 1/2 of that, so we have 4 poles of 2-pole pairs, so we call it the second order. The 5th order simply means we have 5 pole pairs, or the magnetic field distribution changes from North Pole to South Pole to North Pole, South Pole 5 times in the whole machine circumference, so we call that the 5th order or the 7th order. That's just how we measure the space, the wavelengths of that order harmonic.
Okay. I think we're pretty much at the end here. I just wanted to just invite Ved in to see if you had any other comments for Nanjun, or a question or a closing comment.
No, thank you very much, Nanjun. I think there are a couple of more questions. Just with the respect of time, you can probably look into the chat and try to answer them, the questions, and we will move on to the next session as such. And thank you very much for that. So all of you, we do have an exciting session coming up to next in a couple of minutes by Dr. Bullen from WEMPEC. And you can go ahead and join that session in a minute. Thank you.
Right. Enjoy the rest of the week. Stay safe. Have a great day.
Thank you, Nanjun.
Thank you. Bye-bye.
Okay, bye.